All right, onwards to part C of homework 2. If you remember last video for this homework 2 series, we were actually talking about the Crank-Nicolson differencing. Remember that, I'll just go back to it. So homework 2 part B. We derived and used von Neumann's stability analysis for our derived time-dependent equation. After discretizing, of course, we substituted our e to the ikx and Euler identities to eventually solve an inequality showing us that, I think my, sorry about that, it looks like it froze a little bit, but you can kind of see here that we had an inequality that showed that our R was actually limited by a value of 1/2. Remember that R was equivalent to our thermal diffusivity, if I can find it here, times our time discretization over our spatial discretization, somewhere here. But basically, we were limited by our thermal diffusivity, and because of that, you could only really change our time and our spatial differencing or discretization, our change of x, that infinitely small x amount that we were dividing our uniform bar into for our thermal diffusivity. And because of that, you kind of had to find this ratio where in one case, if you tried to increase your R so that you were looking at a more finely spaced, spaces, you would have to kind of multiply your time by a factor of, well, if it was increasing by a factor of 10 on the bottom for x, remember that x was squared, so that factor eventually made our time difference, I think it's right here. Yeah, so that factor, if change of x was 10, you were increasing that, so you could look more finely, then your time would have to increase by a factor of 10 squared, again, since the x here is squared. So I think I posed a question at the end of the last video saying if we're actually limited by this R value, and the answer is no. There's something called Crank-Nicolson differencing. And if I switch over to the Wikipedia here, you can see that this is pretty much our equation, except now we're taking an average where it's not just the current time, now it's the next time period, as well as now we're summing the two together to, well, now it's a average. So we divide by 2, again, moving this over, remember that R is equal to our relative volatility, where here they have a constant, times our change of time discretization over 2, and then our spatial discretization squared. So yeah, basically right here. So yeah, R is basically not changing by that much, but now that what we'll find is we have to kind of isolate these two. We have two different spaces in time, I guess. Well, we have one n+1, and then also at the nth time. So well, eventually using the von Neumann stability analysis, we can show that our values in this expression will allow us to pick any R that we desire. So let me switch over. Go. Yeah, I'll go ahead and just I'll rewrite what we had before, since we already derived that. Remember, we were coming from this equation of our change of temperature with respect to time. Again, these are partial derivatives, had our thermal diffusivity, and then our second derivative with respect to position, obviously squared. I guess what's also important to note is the temperature profile that we also derived in the previous video. We found that we had two exponents. One was showcasing this thermal diffusivity, such that when we took the derivative with respect to time, it also included this second derivative with respect to position, and that was just our imaginary number times k, any scalar value that we multiply our change in x. And remember that these t and x's, this time and position, we denote these as equal to the number of time spaces we're taking and the actual discretization steps that we have. So again, for t, that's n times change of t, And for x position, we note that with the j, and obviously our change in x, delta x. Okay. Go ahead and rewrite this. Remember our time discretizations that we did in the previous video. It went something like, so t, I believe it was n plus 1, j. So at the next time period, at the same position, for the same position at the current time period over our change in t. And this was equal to our thermal diffusivity. Then we had all of this at the current time, but we had the current position, or I'm sorry, the position to the right, minus 2 to the position at our current position, and adding onto that our, again, at the same time, and at the position to the left. So again, nothing new, just everything, reiterating what we did in the previous video, except now, if we want to do the Crank-Nicolson, we have to add that for our second derivative, the right-hand side, we're now doing the Tn plus 1, the temperature at the next time period for these same positions. And we add those two together and then also do an average. So I'm going to kind of combine a few steps here. Oh, I'm sorry. We are missing a over delta x squared here. But eventually we know that these terms are the variable we've been using. So I'll go ahead and I'll keep the left-hand side the same. So we'll just take baby steps here. So rewriting that. Again, this is our time discretization, as well as our, so now instead of just over our position, we have 2 times that since we're doing a average. So same exact thing. Now we'll have, and again, this is a addition. Well, average is addition of all the components divided by the number of components. So theoretically, I could write this anyway, but let's just stick with what they had on the Wikipedia. So that was at our next time period, and all these positions are the exact same. We're doing the same exact thing, just at the next time period. And you'll notice that eventually what this becomes is a group of simultaneous linear equations that we will have to solve. Linear because there aren't any powers or any square roots that we're taking of our dependent variable here. So rewriting again. And then, or if you can see, I might just group these all together. So remember that I'm just writing these under, but they're actually still part of the right-hand side. So again, we're just rewriting from the top here. This is a plus, and then we have, again, at the current time period for the same exact times. So what we'll want to do here, I believe, what are we doing here? So we're expressing it as the algebraic equation with Crank-Nicolson differencing. So all that's doing is now we're adding that n plus 1 term to the right-hand side with all our temperatures. So again, at the same time, so this is just the exact same of what we did before. But now we want to include this n plus 1 term. So I'll kind of say right now, I mean, it should be obvious, but again, earlier we mentioned that we are combining the thermal diffusivity times our time discretization over 2, and then our position squared. So I'll just rewrite that as R. So if you see that, that's where everything went. Yeah, I'm going to kind of combine 2 steps here. So I'll move over the TNJ to the other side. So that will be a plus, and then we'll have a R here. So this term plus this term. And then I'll also be moving over our, you know what, let's just stick with that. Maybe not take too many steps. So again, that was, I move this over, T n plus 1 at the current position is equal to at the previous position or time at the same position plus R. So we moved over our time. That's how we got our R. And then just copying down everything here. I might just do this. Let's go something like this. And maybe let me, just to save time here. And that plus our second term here. Man, if I knew I was just gonna rewrite it, I might have just moved it down, but oh well. Hopefully you can still see that. Oh, we're just gonna move all of it over here. Like so. Hopefully that's still visible. And then now what I'm gonna do is isolate all our like terms together. So you'll notice that we have n+1 terms on the left side and n terms on the right side. So I'll do just that, isolating in our big parentheses there on the right. We'll move it all over. So we'll have something like t n+1j minus r. So what I'm doing is I'm going to distribute the r, basically something like this, where both of these parentheses are multiplied by r. So if we move it to the left-hand side for our n+1 terms, we have a minus r, and that all of those t n+1 terms. So again, copying that down. And then we'll have the same thing on the other side. So that should not be a 2, but just with the n terms. So I'll try to be quick here. And then what you'll notice is that we can eventually factor out our base term, the like exponents. The exact same thing here. Hopefully that's all right. So yeah, we'll factor out this tn+1j term and then the tnj from the right side. You'll notice that they are kind of mirror images of each other, except the signs are a little different. So just pay that close mind, I suppose. So we'll factor this out. We have tn+1j. Factoring that out gives us a 1. And then from the parentheses, we have minus r. So yes, so we're going to factor out all of these n+1 terms. Now we're left with the j+1, j, and j-1. So you'll remember that those are, we'll be using the Euler identities, and also our defined definitions of time and position. So I guess on an aside here, if you remember from the previous video, our temperature, did I already write that? Yeah, I did. So we had our base, and the only thing different from this other term with j+1 and j-1 is this +1. So I guess I'll do a direct comparison. If this is j, I was believe negative alpha k squared t, and then I guess technically it would be this, and then ikx, imaginary number, k, the arbitrary scalar value, and our change in x. I'm sorry, is that we had a j there? Me. So remember when we added a j+1, this was the exact same as our base tnj, except now we had a j+1 here. So the extra value that we are left with is this. Again, literally plugging in j+1 in here would net us something like so. And when we distribute that, we're left with something like our base multiplied by a leftover without the j. So hopefully that makes sense. Again, cover this pretty intensively, maybe too much in the last video. So that's what we'll be doing for the j+1, and then simply with j-1, you're adding a negative up here. So do just that, kind of do all of those at once here. So with j+1, we factored out tj n+1, and now we're left with the e with the extra ik delta x term. Then -2 just comes out since that's the exact same as our base here on the left that we factored. And again, with the j-1, you just have a minus sign here. I'm debating whether or not to do the right-hand side. I guess we should, but it's basically the exact same. except the sign in front here is different. So it'll be 1 plus r, and then the exact same, since these j terms did not change. Only the n terms, and that is not relevant here when we're plugging in for our delta x term with our exponents. So copying that down. And again, remember that we've seen these exponents before. This actually comes from our Euler identity, where if you remember what EIKX, and I believe we just did KX, or no, I think we did something with our K. Again, K is just any arbitrary value. Remember that our temperature profile had an infinite sum where all of these Ks could be chosen, but they were restricted. And as well, there was a constant in front of these expression for our temperature profile. And that constant C and this constant K, all it could be chosen for any number or any real number, but that was restricted by our boundary conditions, in which case those had to be real numbers at the start and obviously at the end. So enough of that tangent. Remember that our Euler's identity was something like cosine kx plus I sine kx. And we found, again, in the previous video, subtracting, or I'm sorry, adding these together with a negative exponent up top would net us a 2 cosine kx. And that had to do with cosine being a even function, resulting in our addition of the 2 cosine terms, and then the I sine, obviously it's odd function, so they would cancel each other out. So we're gonna do just that, and then we'll eventually be able to factor out a 2. I'm gonna go ahead and refrain from writing the right-hand side for now, since I'm going pretty into detail on the left-hand side, but remember here it's the exact same. So I'll do a little at a time here. Again, this was 2 cosine x with the exponential terms. So 2 cosine k delta x is what we're left with after doing the Euler's law. And then minus 2. Then you'll see that we can factor out the 2 here. So, just some basic algebra. And then we're left with k delta x minus 1. So it's the exact same here, except now you'll notice the only difference is this 1 plus r. So I'm just going to copy all of that down as a 1 plus 2r here. And that is at the current time, not the previous time. 1 plus 2r, and then cosine k delta x minus 1. And you'll notice that's the only difference between the two, that sign, as I mentioned before. So moving forward, I'm going to kind of get the same expression as what we were going for in the when we did the von Neumann stability analysis for our original differencing, the backwards differencing. So I'll move it over to the right-hand side here, and what we're left with is almost kind of like I wouldn't say inverse, but they're very closely related terms that are nearly identical. And I guess what's easier to see here is if I distribute this negative. Oh, we are missing an r here, so that is my bad. The cosine k delta x. And the reason why I'm going to distribute a negative sign here is so that we can kind of see why this term will never exceed 1. So in doing so, I'm going to just focus on this term here. So distributing the 1, actually we can rewrite the whole term. So it will be dn plus 1j is equal to tjn. And then distributing the negative, we have 1 minus 2r. And then we distribute the negative, so it becomes cosine kx. And then same thing on the bottom. So this kind of makes it easier to visualize what I mentioned before. You'll notice that this term here, we'll call this y, and this term y will never exceed or is always greater than 0. Remember that r is always greater than 0. You can't choose a negative time step or time scale. And also we're limited by our thermal diffusivity. So whatever material that's already a constant, And then remember that 1 minus cosine kx, this can only blow up to, or not blow up, but we have two different results we can get. Remember, this oscillates between -1 and 1. So the only possible scenarios we have are 1 minus -1, which is 1 plus 1 is 2, and 1 minus 1 is 0. So obviously if it's 0, if y is 0, then we just have 1 over 1. That's perfectly fine. It just won't change. And the main thing here is to make sure our function is stable. So we don't want it to exceed 1, in which case we're kind of having an infinitely large iteration for our temperature profiles. So the worst possible case scenario is obviously this 2 here. So we'll be substituting that 2 in place of the 1 minus cosine kx. And what you'll notice here is that with that being the case, we have 1 minus 2r, and we said this worst possible case scenario was 2, and that was the exact same thing on the bottom. Well, obviously, if r is a positive value, this thing cannot blow up to something greater than 1. Obviously, you'll have negatives here, like if I plug in 5, so 1 minus 4 or 5, that's 20, and 1 plus 4 or 5, also 20, so we have 1 minus 20, what is that? Negative 19 over 1 plus 20. Obviously, you still have a negative value, but this is technically, after you take the absolute value, this is still not greater than, but less than 1. So you will never have a value greater than 1 with our Crank-Nicolson here. So that's that. Kind of moving on here. Now we want to show that it's stable, so that's exactly what we did. Again, for the choice of R, your choice of thermal diffusivity, alpha is limited by your material. That's just a constant. So now the only thing you can choose, I don't know why I did that, is your time discretization and your spatial discretization. So any numbers work for those, as long as, I mean, your R is always going to be a positive value. So whatever the case, our expression here will never exceed 1. Okay, so now we know that that's stable. We're going to go ahead and simulate, obviously, this in code. So when you're solving this Crank-Nicolson differencing, this will be a case of, like I mentioned before, linear simultaneous equations. And to do that, we'll be using matrices and linear algebra to solve those. You have 50 unknowns, you'll have 50 equations. Basically, you're plugging everything on the right-hand side into the left-hand side as you kind of iterate over and over and over again. And that was with when we isolated our terms here. So I'll kind of go back to this. Yeah, I think I might just copy this since this is how we're going to kind of write our matrix. So I'll go ahead and copy that. It grabs everything here. Copy. And we'll go down a bit. Nice. Okay. So I'm gonna kind of write this in a way that will let us write our matrix easier, so we can visualize each row and column. So I'm going to kind of combine like terms again, but I'm not going to substitute the exponentials. All I'm doing is combining like terms. So what we'll have here, we'll focus on this term first. So that's just simply minus r, different color, minus r n plus 1. So again, at the next position, or the at the next time period at the next position, then we have like terms here. So what is that? 1 plus 2r, because of this negative sign. Negative negative makes a positive. So we'll do adding a 1 plus 2r. Then that is our base, n plus 1j. And then again, same thing for our previous position, it's just minus r times that. So minus r times at the next time period for the previous position. So same exact thing here. You'll notice just the signs are different. So again, try to match up here. So r times our base at the next position, and then we have, what color did I use? Pink. So we have 1, -2. This is a positive, so it's just a -2. So we have 1, -2r. Did I write r on all of them? Okay. And our base, current position at the current time. And then all that's left is r and tnj minus 1. So we just multiply those straight across. Kind of evaluating the parentheses and simplifying. So, believe it or not, this is our matrix. What we're going to do is this will eventually become a row of diagonals here on the left-hand side. We call that a sparse matrix, or I'm sorry, banded matrix, because of the 3 bands that you'll see that are the diagonals. And this will also be known as a sparse matrix, which is pretty common in engineering, where most of the equations only depend on a few unknowns. In this case, it's just these 3 known variables. And for the rest of that row, you'll notice that it is pretty much 0. I don't know if I should space this out a little so we can kind of see as we go along clearly where each thing is going. So I'll kind of space this out like so. Hopefully that's enough. I'll add some more space here on the left hand side as well. Okay, so this is our matrix. I guess it might be helpful to write, I'm going to head and move this up and then show our bar that we're going to be discretizing or discretizing. So let's use blue. So we have a bar. This isn't obviously going to be to scale, but there's going to be a lot of slices here eventually. But what we'll have at the very end, obviously we're indexing from 0 to, let's do n+1. So that way we can say the last term here right before n+1 is n. And that way we can say that we have n number of unknowns. So that's the number of sections we're going to be dividing. I believe in our case, our problem says we want to do 20. So at 20 Celsius, to discretize the bar with 20 time dependent temperatures. So our n will be 20 in this case. Big N, not to be confused with our time indexing. So that will be n. And obviously our n's here are known. So this is T0 and obviously Tn+1. And then we have Tn unknown temperatures. So this will be our matrix that we'll be solving for. But let's focus on actually writing down our matrix. So it's something like that. I'd make this as big as we can. Then we have our temperatures. And then this is equal to our right-hand side, which you'll notice is just, will be the same dimensions as, well, we're doing a dot product. So I guess the best way to visualize this, remember that matrices are denoted rows, columns. So I'll be writing them something like this, where I is a number, J is a number. In this case, we'll start with something we know. So T1, T2, T3. Remember that we know our initial T0 and our Tn+1. Obviously, this will be Tn. But this is simply a 1 column vector with, well, it's n number of, it's all our temperatures, so it's n number of rows. So this is a n rows by 1 column. And then for here, well, we're doing a dot product. So all these rows need to match up with, I'm sorry, all these columns need to match up with all these rows. So in that case, we know the number of columns has to be n as well. But how do we know how many rows there are? Well, that's just simply the number of iterations we're doing. So it'll be, well, it'll just be iterations. And hopefully this becomes more clear as we progress through the matrix. But remember, now the dot product, the matrix that comes out of this dot product is just the outer bounds. So it will be iterations by 1. So that's the dimensions of this matrix. Okay, so kind of lining things up here. Wish I could draw a straight line, so I'll try my best. Something like this. Hopefully that's okay. We want all these rows to match up as best we can. So something like that. And remember that all so that's for the rows. All the columns will be matching up to each temperature that we are solving for. So this is kind of right here at the top, T1, T2, T3, and so on. So writing with something we know, again, we'll start with the middle here, pretty much the easiest for T2, so J equals 2. If J equals 2, well, what are we doing? It's the left-hand side. So for T2, at J equals 2, at T1, so if we plug in 2 here for our previous term, T1 must be multiplied by negative R. So we put a negative R right here. Let's pick a good color, something like that. Maybe let's go pink. So negative R. Again, plugging into our left-hand expression, what should T2 be? Well, T2 is the index we're at. So J equals 2. If J equals 2, T is 2, obviously. So at the next position, we must be multiplying by 1 plus 2R. So we'll write that down here, 1 plus 2R. And then T3 is the position to the right. I might want to move this up a little bit. So something like that. So again, J equals 2. So if J equals 2, it must be 2 plus 1 is 3. So at the next time period, at T equals 3, well, this T3 must be multiplied by negative R. And you kind of see, well, let's move on to T3 as well. Well, the rest of these are zeros. We should mention that as well. So something like 0. That should be good. We'll just keep it as ellipses for now. We can actually add another term here, or another column. So these are zeros, again, because our expression only depends on 3 terms, where our center at J, the position we're interested in, so zeros. T3, going something similar. Well, what is T3? I'll add a T4 here so we can see the next position. But at T3, our index is 3. And I don't know why I cut off here. T3. So if our index is J equals 3, well, our position on the left, well, actually, let's start with our position that's known. T3 is right here. So T3, our known position is 1 plus 2R, again, given by the middle expression of our left-hand side. And we know the sides to it must be negative R. So at J equals 3, T3 at T2, the previous side here, must be negative R multiplied by negative R. And then at T3 again, at T4, so J equals 3, that's our index is 3. At T4, which is this term, J plus 1, it also must be negative R. And again, all the rest of this row is 0. So the interesting part for a matrix here, you'll notice that eventually you form diagonals coming down with these 3 terms. But at the very end, where we have T1 and Tn, eventually, you'll notice that, I guess this is T1, obviously this is Tn. You'll notice that if we try to do something outside our matrix, well, the term to the left of it, the J minus 1 term, in the case for the J equals 1, that is a known term. We can't put that as an unknown since it's technically not in our matrix here. So what we end up doing is something like this. Let me get rid of that. So let's just do it how we have been doing it. At T1, J equals 1. Well, our current term is T1. We multiply by 1 plus 2R. The term to the right, J plus 1, again, negative R. But you'll notice that there is no space for this negative R for T0. And that is because T0 is a known value. Again, we said it was outside the our temperature profile, our unknowns that we're solving for. It's actually a known value. So instead of what we normally would put a negative R here, we add it to the other side. So that is still basically the same equation. We're not losing out on anything. by doing that. So I add that to the other side here. That way we still keep that expression without kind of cutting it off on the left hand side. So that was color they use, pink. So that was plus r t naught, or t0. And remember that t0 is a known value. So again, coming down here, what I mentioned before, well, at n, now the j plus 1 term, or n plus 1 term, is a known value. So you'll notice that we don't have space at the very bottom here. It would be something like at the very end, we'll say this is tn, and then somewhere along here, tn plus 1, just like how we did at t0. You'll notice that there's no room for a r. Should have kind of drawn this out a little more spaced out, but that's okay. So that's r. We had a 1 plus 2r term for our current value, since that is known, or that's still within our matrix at tn. I guess these two should basically still be matching up. So let me fix that. Should be, so this is r, and this is the, oh, I'm sorry, 1 plus 2r. And note that it looks a little confusing, but remember that this is not in our matrix. That should be negative r2. And then at tn minus 1, that is a known value. So that is still negative r here. So again, since it's not part of our matrix, we add it to the other side. So that's negative r times tn plus 1, where we add it to the other side, it becomes positive, in which case we do plus r tn plus 1. So those will be hard-coded into our matrix as we're coding this out. Eventually what we're going to want to do is code out our diagonals. So obviously we have zeros coming down, zeros coming down. These continue all the way until the very end. I guess I didn't draw this to line up, but the negative r should line up with the diagonal. But hopefully we get the point where we have a bunch of zeros. Again, a sparse matrix. Contrasting with the dense matrices that we have, like system equations when we first learned those in like middle school, high school. The big difference is with dense matrices, like the ones we learned in high school or middle school, those usually have coefficients for all the variables. In this case, this is a sparse matrix in which the coefficients aren't known for all the variables. They're mostly zeros or omitted entirely. So hopefully you get the point. And we're going to go ahead and code this out. And I should note that with coding this out, so we'll have our a diagonals. I believe the function we're using is solve banded. We have to, we'll provide an interval of our diagonals, so how many diagonals are on top and how many are on the bottom, so we can decide, kind of denote which is which. We'll provide it our a diagonal, so this entire matrix here is our a diagonals. We'll provide it another matrix B. Technically this is actually AB, but changing the name because why not? And then it will solve for us, that function will solve us our unknown temperature profiles. Also, I should note while I'm here anyway, well, actually I should finish doing our right hand side as well. So with our right hand side, that's obviously our right hand side equation up here. So now move that over and kind of note that this is just many rows, but any number or one number of columns. So all of this is just one line, in which case, again, the dot product is the sum after we multiply our column here by our row here. So hopefully that makes sense. We'll go ahead and evaluate our right-hand side. So remember, we're going to keep this plus r t0 since it's a known value. We didn't have room for it in our matrix on the left, so we add it to the right. Kind of just makes sense of balancing. So let's keep it this color. Again, at t1, so where are we? We just plug in our j equals 1. So if j equals 1, this is simply just t1 to the n at our current time times r plus 1 minus 2r. t, again, we are at time 1, or j equals 1. So I'm sorry, this is wrong. If j equals 1, obviously this term up here, it must be 2. So let's fix that down here. 2. And then again, at the current time, j is 1, so we plug in a 1, and then we have our term again, so our previous term, so that is our known value Tn 0. And you'll notice that we can actually cancel these out. Actually, this should be a n as well. You'll notice that we can cancel these out because, or not cancel these out, you could group them together, but I'm going to refrain from doing that since it kind of omits the whole purpose of these special cases where we're at the top and at the bottom. So again, we'll do it for 2 and 3 just for some more practice. So hopefully this starts making more sense. So at T3, our next position, or T2, our next position is T3, plus our 1 minus 2R. Again, at the current position, j equals 2, so T2. And then our previous position, which is T1. And then same banana. Next position, and then current position, and then previous position. Then now we can come down here. Hopefully everything is making sense. Exact same thing, except now our index is j equals n. So if j equals n, our next position would be r times t n plus 1. I'm not sorry. That should be tn, and then next position is n plus 1. Yeah, big N plus 1. Kind of confusing when you both have the mens, but oh well. So now we're adding a 1 minus, right? 1 minus 2r coefficient to our previous time period, or our current time period, which is our current position, I'm sorry, which we index at n, so it's just n. And then we add our next time period, or previous time period. I keep saying time period, it's position, which is just n minus 1 at n. So keep in mind, these are the known values that time dependent or time independent. So you could kind of say something like at j equals n, you have your previous your temperature at the future time period at the same oh my goodness, at the, that should be a small n, so your temperature at the next time period at your position n, I guess n plus 1, is equal to your temperature at the previous time period at n plus 1. Remember that n plus 1 is simply just our known value. I believe we have 80 for the right hand side, so n plus 1 is, I guess, 20. It'll be the T20 since we have 20 indices for n. I guess it's technically 21, since if we have 20 unknowns, then you have extra 1 you're known that you're keeping constant, and the extra edge that you're also keeping constant. So I believe this is 40, and this is 80 in our case. So technically you'll have 22 total. This is another one, this is another one. So this will actually be 21, or 22, if you want to think of it like that. But technically it's just 80, so hopefully this isn't too confusing. Again, for the left-hand side, we had j equals 1. So at j equals 1, our time period at the future time period at the same position 1 is equal to, I guess it's technically, well, it's j minus 1, so it'd be 0 is equal to the current time period at 0, and we know that's just constant 0. So index 0, that's a known value, that's 40 on the left-hand side. So 40 and 80, those are known values. They're time independent, so we keep them constant. That aside, I also wanted to cover how we're going to code these diagonals. Oh boy, what happened here? Hopefully that focuses in. So we'll start, give a quick example here. So something like draw rows so looks more coherent. Something like oh, I need my columns as well. So we have A, B, C, D, E. Maybe 1, 2, 3, 4, and then 5, 6, 7, 8. So those are our diagonals. You'll notice here when we write this out that this number of elements, it's 5 in this case, but the diagonals only have 4 if you can just count them. So in which case, to fill out the rest of those empty spots, we use zeros. So this will be 1 0, so it still matches this column, and this will be another 0, so it still matches this column. Okay, so we'll do just that. So we kind of read it left to right. So if I drew something like this with arrows, that kind of turns into, we kind of put, it's not another matrix, but we orient it again to look like that, so it's just straight lines across. So reading this out, we have 0, 1, 2, 3, 4, and then A, B, C, D, E if they're pink, and then 5, 6, 7, 8, 0. So again, these zeros are filler. Technically, they don't have to be 0. They could be any number. I believe in the for the function, or I guess the documentation, I guess, they use asterisks to denote those values, but with zeros, since that's what I'm used to, and that's how I learned it. So let's work with that. Again, zeros. And then one more thing to note, if we had another diagonal, in which case our matrix only had 3, but if you had another one, just for whatever reason, I don't know, fill it out with, I guess another, what are we at, 8? So I know 9, 10, 11. We reach the bottom of our matrix, and then we do 0. So again, we're outside, but we still want to match this column. So it's 9, 10, 11. And actually, we're missing another 0 here since we want to match the other. So we actually didn't reach these last 2 dimensions of our matrix, so that's why we add 2 zeros. And you can see those 2 zeros right here. Okay, so that's how we'll code it out. I don't think I'm missing anything else. Hopefully that all makes sense, since now it's the hard part. Well, hard part for me at least, so let's hope I don't mess up here. Again, we're doing a uniform bar, 20 Celsius. So our 20 unknown values will be 20 time dependent temperatures. So we'll discretize 20 unknowns into 20 Celsius, and then 40 and 80 on the left and right hand side respectively. We'll do 100 time steps and then plot in time 10 time step interval. Oh. Let's do it. Let's go to lab, and I'm just gonna go off our previous work that we did in the previous video. Hit run all again. 30th. That was like 3 or 4 days ago. Okay. Yeah, I don't know why I was calling that before initialized. So go ahead and graph this, pretty please. Okay, still working. And we still have the same position line width, so I might change those. I'm gonna go ahead and import SciPy as SP. So when I type in the linear algebra line, it doesn't sound as, or look as long like water, since I've been talking a very long time. Okay. I don't think the R is specified here, but I can't remember if, oh, I'm sorry, we do use, so it's R equals 2 for R values, but I'm just gonna work off this template so I can still copy paste this code for graphing since I'm kind of lazy. Yeah. So let's go ahead and define what we know. So we have our right and left temperatures, which stay constant. So I'll do T left is equal to 40 Celsius and T right is equal to 80 Celsius. Those are held constant. And then we have our T initial values. Those are our 20 temperatures that are held constant at 20 Celsius. So we use something called MP full. That's simply, I think we've been using this in separations, but anyways, this is just, oh, it says it right here at the top. We need to provide a parameter of a shape. So how many, I I guess, instances do you want of the value, and then the actual value that we put in the second line, our second parameter. So I guess what I should do first is also define our n, our number of unknowns. So we said that was 20, and then I will provide it the shape of 20, and then funny enough, our field value is also 20, so that's 20 Celsius, and we should go ahead and look at that first. Why not? So yes, it's 20 instances of 20 in an array. So if I do dot shape, it should tell me 20. Yep, just so one-dimensional array of 20 elements. I'll also go ahead and define our R value. So I think it says 2. Shift enter on that. While we're defining stuff, so I don't forget in the future, eventually what we're going to want to do, so after we define our AB, oh no, what happened to my camera? I just noticed that. Did it turn off? I'll pause and fix this. Okay, so this is very sad. Apparently I've been recording or talking without recording, so I actually don't know where I left off. So I'm gonna go ahead and delete all this. I think I did not do any of that before I stopped. Hopefully I left off here, kind of initializing our variables, but I'll kind of re-explain it just in case. Again, defining our left and right hand side, those are time independent, so we keep them constant. Our number of time discretizations, n equals 20. R equals 2 given by our problem. That's just what we decided what it was. Initial, I am creating an array, a full NP array of size n, so 20 elements filled with 20 variables. So that's what this is. And then t history and t old, I remember that was mainly for me, so I didn't forget to put them in. But for t history, we're going to append all our new temperatures in this profile or in this list, eventually turn it to array, and then combine them with our left and right hand sides to form the full temperature profile. T old is an initialization of our what do you want to call this, in our loop. So we're going to iterate our loop to kind of evolve our temperatures. Obviously right now we're at our baseline here, and this is our temporary temperature, which is going to be used for our B matrix. Hopefully I explained A and B yet, but if I didn't, for solve banded, we have a couple parameters. We have our where am I? We supply a tuple of our I guess intervals, are not intervals, but our lower bound and our upper bound diagonals. So this is just 1 and 1, since we have one upper diagonal, one lower diagonal. AB is our banded matrix, so that's the A diags that I coded out and deleted because I didn't explain it on video. And then B is the right hand side, which I'll also code out, and that will be dependent using this temperature T, where I will be indexing the current temperatures, the temperatures to the right of those temperatures, and the temperatures to the left. And that's what will be used for the right hand side as we store that in our loop. Hopefully that all makes sense, and double checking I'm recording. Okay, so for the second time, let's do, we're gonna make our diagonals. Again, remember from a OneNote, man, I really hope I did that on camera. I'm pretty sure I stopped when I started coding, so I'm pretty sure at the very least this stuff was on camera. So anyways, we're going to be writing our diagonals. Remember our diagonals are missing one variable, or I'm sorry, one element from the main diagonal, since they go outside the matrix at these points. That's why we have these zeros at the end. Again, looking at our actual matrix, we are missing a negative r here, because technically it goes up above the matrix, and another negative r down here since it goes below. So we plug in zeros there so it matches the number of elements in our main diagonal. Okay, that being said, go ahead and code this out. Let's start with our, eventually I'm going to plug it down into here, our A diags. And how do you want to do this? Well, why is it? Well, I'll plug it into there later. So we have, again, be using NP full. So we want to supply a shape and the actual elements that are going into that array. So we'll start with our, I don't know, diag middle, diag center, middle diag, upper. Yeah, let's go middle. always in names. So middle diag, what is that equal to? It's just simply a full array. We're not taking any elements out or adding elements in. So a full array of our unknowns, since the number of our unknowns matches the number of elements in our middle diagonal. So let's kind of get that here. Again, 1 plus 2r correlates to every single current position temperature for all our unknowns. You'll notice that it appears for each temperature 1, 2, 3, all the way down to Tn. That is why we just supply Tn for our number of elements, and then we add in, what is it, 1 plus 2 times r, and go ahead and display that. Yep. So again, r was 2, so 2 times 2 is 4, 4 plus 1 is 5, and then it should be 20 cases of 5, 20 elements, I guess, or 20 instances, however you want to say it. So that's the case. Awesome. Very next thing we'll do, upper diagonal and lower diagonal are fairly similar, but you'll want to notice that we will need to add a 0 at the left-hand side for the upper diagonal and right-hand side for the lower diagonal. And the reason for that is, if you remember of our notes here, when we are writing our diagonal down here, the upper diagonal had a 0 on the left. That is because we are missing a dimension. Remember, it extended beyond our current matrix. And our bottom diagonals also had zeros, but on the right-hand side now, we are matching to fulfill the same number of elements as our original by adding to the right-hand side, again, because they are outside our current diagonal. Okay, so what is that? I'll do it the wrong way, or I guess a way that's missing those zeros, so you can kind of visualize this, but this is n minus 1, because we are missing one parameter, or one dimension, and then we want to fill those. Those are all negative r's, so if I go ahead and display this, they are all negative 2s. Again, r is 2. So now I want to concatenate them along the row, I believe. The row, yeah. I always get them mixed up. So with the concatenation, use the list brackets, and upper diagonal, we do, I said 0 on the left. I'll do just that, and it should add 0 there. And now you'll notice that this is a shape of 20 elements versus before. I don't really want to delete it, but before, obviously, it's 19 since we're adding a 0 here. And the case that we want to do is, obviously, we want to match these up so that when we do a vertical stack, when we stack them, all the arrays on top of each other, they all match nicely. Again, lower diagonal, very similar. All I'm doing is moving this 0 to the right because, again, it's the lower diagonal, so we add zeros to the right. So I do Control-Shift-L. I'm just going to change the name to, can I just click on this? No? Okay. Let's do bottom. Okay, whatever. Bottom diagonal. I guess lower, upper, lower. So upper diag. Jeez. Lower diag. And we concatenate along the row, but this time we add 0 to the right-hand side. Our recording. 20 elements, and check, it should look the exact same, but now 0 on the right. Awesome. So all I'm doing here is adding the variable names. I know in class we kind of just I'm merging these. In class we wrote all the variable names just as is without actually assigning them names, but for me this helps me kind of keep track of what I'm doing. So as we vertical stack, obviously upper diag, middle diag, lower diag. So that's how we stack these vertically. Remember to actually stack them, and I want to supply as one element or one array. So it is upper, middle, and now lower. And now if I go ahead and display that, there we go. So we have upper, 0 on the left, middle, 20, and then lower, 20 with our 20th element we added as a 0. Awesome. And that was all on camera now. Okay. I'll go ahead and merge these. So now we have our A diags, our left-hand matrix. Awesome. All we need now is our right-hand side, which is our B matrix. And the way we're going to do that, let's switch over. So, hope I'm still on here. The way we're going to do that is by using the T initial term I mentioned before. So T initial was our entire uniform bar at our current time period. And this is just keeping track of how we're going to iterate it. So again, at T1, I'm not sure if this is, I guess it'd be technically T0, where it was 40 on one side, 80 on the other, and then 20 in the middle. So that was T equals 0. Now at temperature 1, as we evolve, that will be changing. But in this case, I want to kind of showcase what I'm actually doing. I'm going to be using different numbers from 20, the 20 constants, so that you can actually see what's happening. About how I want to do this. The initial. So T initials here. This will eventually actually be T old. So I don't know why I left it like that. I'll make more sense when I actually write the loop, but right now I'm just making sure it's right. So we'll be using temp T. Again, temp T is our uniform bar, the entirety of it. So the B matrix is essentially the modification of this as we use so we have, this is indexing again. So it's 0 to 20, or I guess 19. And then we are indexing from element 1 to element -1. This is our, again, the initials. But for the positions on the right-hand side, we shift over 1. So 1 over is 0, 1, 2. So 2, and then 0, 1, 2. Again, this is just 2 to the very end. And then going back to our unknown positions, or I guess our T initial positions, if we want to get the previous position, we shift over to the left. So instead of element 1, we go to element 0. And this just simply goes up to here, in which case we just write the colon, so signifying we start from the beginning all the way to -2. Since, again, this was the starting point, this is the previous positions. Hopefully that makes sense. I'll be using temp T. Actually, I said I wasn't. Or was I going to use T initial? I don't want to do this. Let's do, I need to remind myself. I'll just comment it out, but it should be the exact same, but I'm going to keep it the initial. I think that's why I had it initial at first. And then I'm going to change the T initial to something that we can see that's actually changing. So T initial will be something like an MPA range of 1 to 21. So that should be 20. Let's double check that. Oh yeah, it does it here. Awesome. Yeah, so when I actually index them, you'll see what's happening. That's the whole point of that spiel. I'll make a note, take out comment, and then remove. So I know what to actually remove when we fix this for what it is. What are we doing? Temp T. So I want to grab, so B will eventually be that entire equation you saw before. The recording. It was, where's my mouse? This and this. So it's this whole equation here. Oh, that was blurry. So that's what we're typing out. But to grab those indices, right here. So you see, notice how they're changing. T1, T2, T1, T0, and then T3, T2, T1. Well, those are simply from here. Our future positions, our current positions, and our previous positions. So to do that, we're going to do some index slicing. And that's what we're about to showcase here. So I believe T initial, or temp T. So temp T, to grab our, I guess, known positions. So our positions that are in between, we said that was 1 to -1. Again, those are the temperatures that are evolving, that are changing. So that should be 1 through 20. Awesome. And then we want to multiply that by 1 times 2r, or 1 minus 2r. So 1 minus 2 times r. Want to multiply. That's what we get. I guess I should put, I don't know if it'd be more helpful to just see the indexing and then I multiply. Maybe that's more helpful. So I'll remove this for now. I guess I'll comment it out. But again, these are grabbing, come on. Here we go. So these are grabbing in the middle, 1 through 20. I think you kind of get the point. I'll delete that. And then now if we want the future positions, we do, I'll keep it, you know what? Can't decide. It was 2 to the very end. So this should be 1 to 80. I'm sorry. It should be 2 to 80. So if this is our current position, shift over to 1. It goes to 2 and 80. So 2 and 80. 2 and 80. Awesome. And then what's next? Our previous position. So it's temp t from the start to the end, but we stop at -2 so that we go from 40 to 19. Let's remember, this is our positions we're interested in. Positions to the left would shift this over to 19 and then start at the very beginning. So 40 to 19, 40 to 19. Awesome. Hopefully that makes sense. I've done this so many times, I kind of memorized them already. So, I mean, memorize, understand, kind of go hand to hand when you do it enough times, since you know it's wrong. Anyway, since we're writing that all together, it's simply just our expression. What is it? R. So R times, we use R times our future, 1 minus 2R at our current, and R to our previous. So all of those are positive, and then we have to watch out for the parentheses in the middle there. So I'm just gonna go ahead and delete all these. And I think I've made my point with the temperatures. So I'm gonna go ahead and also comment this out again. Comment this out. But I will keep what is this? Wow, now I'm confused. Okay. So I believe now we're using our original initial temperatures, and now we use T old, which again is a copy, but we keep it this way so we can do the loop of the for loop once we have the B's done. The B matrix is what's getting iterated so that for each loop, it'll solve a new temperature profile, and you'll see that in our for loop. Oh man. What's my time? 9 o'clock? Okay, hurry up. What am I doing? Oh yeah, so I'm going to multiply R times our future positions, which we established was temp T at future positions 2 to the very end. And this was added to 1 minus 2R right there. I already did it. Awesome. Yeah, our known positions are 20 positions in the middle, and then we add that to R again times our previous positions, which was temp T from start to -2, I believe. And I want to, I don't think it'll do that. I need to probably add these values together in a row, I think. Check me on that. Let's try it. Do it. Okay, it worked. What we get? Awesome. We get something. Oh, I didn't evaluate all these. Like that doesn't look right. There we go. I think that should be right. Notice that it is adding twice. Is it adding twice? Our previous temperature should have been 40. I don't know why it's 60 here. Oh, we're multiplying by 2. I see. I think in practice I was doing 1, but in this case, we also want to again add for our jeez. For our special cases, the top and bottom, remember that we have to add another increment of the T initial for the j equals 1 index. Since we added it from the left-hand side here, it was outside our matrix there. And then again for the bottom, we added Tn plus 1 twice. So we're just adding it another time, one more instance, since it fell outside our matrix here. That was the n plus 1. So yeah, so we'll add those in, kind of hard code that in. Here's a good way to showcase the in-place addition. I guess I'll do it both ways. So we increment at b equals 0. So this element, we're going to add in one more time our r times temperature T. I'm sorry. All right, temperature left hand side. So that was 40, and this is the same thing. Let's evaluate this again. So now it's 140. This is actually the same exact thing as if I did the in-place operation, in-place addition. So it just saves extra hassle. So it's still 140 there. So I'm going to do the exact same thing again. In-place addition saves me from writing that extra step of writing the additional element once again. So for the special case on the bottom, we are adding the right-hand side 80. We don't need to add these anymore since it's an in-place addition. And should be good. Let's print V2. Oh boy. Come on. You can do it. There we go. Why didn't you print? There we go. 140, 300. So that was 2 times 40, 160. Am I doing this right? It's basically just times 3, right? Because we add it 3 times. So was it 40 times 3? 120. We have an extra 20 for some reason. I do that right? Let's change it to 1 since I know what it is at 1. There we go. So yeah, double, because we added twice. Yeah, that was right. I guess I confused myself somehow. Very cool. So we have our B matrix. Now we use what I did this for, the SciPy as SP. We can finally put in the function, solve banded. Now we have all our parameters here. We have our upper and lower bound provided as a tuple. So again, one upper, or I'm sorry, lower bound first. So one lower, one upper. So that's just 1, 1. What was it? What is this? linear algebra. Lin-alg, solve banded. Why will you show up? I have to reevaluate everything. I really don't want to do that. Okay, so again, supply L and U, lower and upper. So that was 1 and 1 as a tuple. Our AB matrix, we called A diags, and our B matrix is just B. And solve for us. Awesome. We got Tom playing. I believe this is our first iteration. So again, at time equals 0, everything was 20. Now we have evolved 1 step. Now we're going to want to iterate this. To do that, I'm going to go ahead and combine everything. I think I combine this. Maybe not that, but I will be moving over these, I believe. Yes. Do that. Copy paste, Control X. Put these at the top. Technically, we don't need this, but I'm going to keep it now. And now we have T old. So this is actually going to be our within our iteration. So I'll move this down. Again, remember that we're going to be iterating our T old. T old is initialized at T initial. So T old will be refreshed at T new at the bottom of our for loop. So we go something like for I in range. Did we say 100 steps in our problem? I don't quite remember. 100 times steps, and then we plot at 10. So that should be good. So we'll do 100 times steps. And I'm going to shift everything over with, I think, Control Shift bracket or Control bracket? Control bracket. Okay. What else? So this is T old. I think we're missing a. I think this is right, actually. So temp T, and then after we solve it, actually we want to store our new line of temperatures as t equals new, so t new. And then I'm going to add that to our history, pretty much appending it every time it's added, or we calculate it, so that append, and then we do t new, and then obviously our t old is now a copy of our t new, again using copy so we don't change our previous initialized array of t initial. So that's that. It's 9 o'clock. Okay. What else? I think that's it. Kind of look at t history. Hopefully, it looks good. Okay. Yeah, something. Yeah. I mean, it looks like it's evolving. We reach a steady state. Let's plot this up. Oh, we are reaching very early steady state, so that there might be something wrong. I think I might be missing something. What would it be though? Probably another copy of this. We're getting to initialize. So we have t old. It's using t initial at the start, and then it gets refreshed here at the bottom. It should be right. And then it's our new t initial in the middle. I'll double check if we find something wrong. But for now, let's go ahead and do this. So I'm gonna want to, for our full t history, our temperature profile, I'll need to v-stack all these arrays since they're all separate arrays in a list right now. So I'll do actually let's look at its shape for now. So mp.array this thing and look at your shape. See if it's doing the correct number. Yeah. So it's 101 and then 20. 20 for our discretized positions, 101 because of 100 iterations, and our initial t initial as the other additional one. So we're gonna need to v-stack. Essentially we'll have a v-stack of our history, so it's not just a list of random arrays, it's one whole, it's rows of arrays this time, instead of just separate arrays. And then also we'll want to add the left and right hand side. So to do that, we'll need to find the same number of elements that our the history has, and we've done that before. We can do that by calling the 0 element of this function, but we can also do that by using the len function, which will allow us to call the number of elements within t history. So that will all eventually be concatenated into temperature. So we'll go ahead and start with I guess t history. Technically, this is a pretty simple step, but I'll keep it as a variable anyway. So I'll call it t history stack maybe, and that is simply just doing the v stack of our list so that it becomes an array. I think I just put t history. It should be okay. Okay, and then calling it should give us all of it. So awesome. So it's not just single arrays for each row, it's one whole array like so. That, and now I also want to do the same for our t left and right. So t left stack, I'll be doing it np full, and this time with the shape using the len function. So len allows us to find the number of elements in our, well, whatever list we have. So t history is our list, so that'll be the shape. It should be 101. Double check that case. Len t history, since we want the same number of elements, awesome, 101. So it'll be 101 instances of t left, and let's double check that. T left stack, awesome. That should be 101. There we go. And then same exact thing for t right. We're adding all our right temperatures right hand side, obviously to the right with the same number of elements, but this time with t right are 80 degrees Celsius. And then to put these all together, we're going to concatenate along the column side now. So np concatenate, and then using brackets for the array, and supply them all at the same time. So t left stack with t history stack. and then T right stack. Let's view our temperatures, see if that's right. Awesome. So we have 40s. I'm really surprised that happened. And it looks like we do have the right temperatures here. Very curious why we found it to, maybe we're too early, or we found the iterations that were all too close to reaching the steady state, because we were at the very end when we were looking through the results. But this is exactly what we wanted: 40 on the left, 80 on the right. So all that being said, now we're going to plot this up. Now is when I get to finally use this, copy paste everything here, and remove what we don't need. Since I coded it all already before in the previous video, I can do that. Don't need any of that. For now, I'm going to Control-Shift-L, change all of these to Fig2. I'm also going to, I think we don't need these. We only need to plot within our range. So this will change, and we don't need to print it either. So what we need to do at the very start, obviously xplot, we need to plot. Well, what is our xplot? It's the x's along the different positions, so that's 1 through 20. The best way we can do that is grabbing from this function, I guess. We're gonna grab the first element, so that second number, second value there. And to do that, we do 1. Don't believe me? Actually, I don't believe myself, so let's check what it is. Xplot should be 20. Awesome. That's next. We make our figure. This is just aesthetic. For range, so now the range does matter. This will be very similar to we want to iterate between all the rows, and obviously the rows are from this function as well. We saw it earlier, it was 101. So we'll do the exact same thing. I wonder if you could actually do len, and it might be the exact same thing. Curious. We'll try it later. So now we're iterating through every row of that temperature of this. And after iterating through every row, what do we want to plot when it equals 10, since we're only doing 100, right? Right, yeah. After every 10th I, so it'll plot 10. 100 divided by 10 is 10. If it equals 0, so no remainders, we plot, what are we plotting? Our xplot, that's why we made it. And then our temperatures, so we want to index that at the I interval for all the, I guess, the entire row. So I guess I could showcase that, why not? So if I have A equals MP arrange 4, and I reshape that to a 2 by 2, shape 2 by 2, come on. And then I say I want to do exactly this, so call A at some number, I don't know, 1, and do the same exact thing with that weird colon. Well, now I'm grabbing the second row. So for every I, we're iterating through every row, and after every 10th row, we graph the row. I'm getting a call here, so I will pause. Okay, sorry about that. Where was I? So yeah, again, this I is just iterating through every row. For every 10 rows, it graphs it, and then now that's what we showed here. If I have an index, essentially doing a index slicing or array slicing, however you want to say it. With 1 this is the placeholder for I. I is obviously the number of rows, I believe is up to 101. So it iterates all through that, and then it grabs the 10th row. So if I go ahead and graph this, please work. No, what am I missing? X equals x plot. Receive value. Interesting. Oh, wait, hold on. Why is this wrong? Do I have to call everything again, maybe? No, it still yells at me. 20 is wrong, supposedly. Okay, I'll go through my code and fix this. Okay, kind of embarrassing. I thought I could go the whole video without checking my code, but I'm looking at T history or plotting T. So very obvious. Why does it keep doing that? There we go. Should be T for all of them. T. Okay. What? It's still this. MP array of T and grabbing the shape of it. One. What is that? Is that not a number? Show me. 22. Wrong? Be 22 values, no? Okay, I guess that wasn't it. This is right, so it's something down here. Do add scatter. All right, pick two. Right here. Needs to be a range. A range returns that interval. Remember the array, and it needs to be in the shape of T. And we grab that. So now it should be an interval or an array. Very funny. Oh my goodness, there's more. What is going on with you, man? True value of an array of more than one element. Use. The heck? And okay. Okay. It's always syntax, man. This. A range of the shape at one. Of the shape at one. This one worked. Oh, I didn't change it down here. Awesome. Okay. I'm tired. It's 9:15. Actually on track. Okay, so what have we learned? I'm not sharing on that anymore, so I'll go to here. So with our video, all our parts, homework part C, we did our heat diffusion and we did our Crank-Nicolson. We did the stability analysis, so you can choose any R. I guess I can show that here if choosing any R in our graph. And then we discretize 40, 80, kept a constant, 20 time dependent temperatures in the middle. That was correct. And R equals 2. And then we had 10 time intervals for 100 time steps. Okay. So going back. Actually, I was curious if I could do len t. No, I don't think that would work because it's not the number of elements anymore. It's one array. Okay. Yeah, I mean, this is it. I guess we could plug in for different values of R, but they might start, while it was stable, it might start oscillating. Really? 5 is no big deal? Is it reaching from there possibly? If I do that. Oh, there we go. Now we get some oscillations. I wonder what I can turn it up to. And that might take a long time. It might blow up too. It's pretty big 10. But anyway, yeah, too big. I didn't even graph it. Hey, okay, it worked. I don't know. But anyway, you can choose any value of R, and it should still work. For your this is our Crank-Nicolson model with our uniform bar. So I guess we plotted up. Hopefully my syntax errors at the end weren't all that bad. But yeah, we learned that Crank-Nicolson is not limited by R value. Meanwhile, our backwards differencing we did in the previous video was, and that was all derived from the von Neumann stability analysis. Now we have a bunch of new ways we know how to code. We're using matrices. We use boolean function for solving a abandoned function. We learned how to stack those codes or stack those arrays together with VStack. And then we appended all of those into our temperature profile, or technically our T history first, and then we did another VStack, or I guess concatenation, excuse me, for our temperature. So yeah, looks like we reach steady state quite fast here. Very interesting. All right. You don't see another addendum from me. It looks like we're good. So thank you. Okay, I lied. One more addendum. So the R values, I guess I didn't explain what we were doing when we jacked this up. So higher R values means smaller x's. We're taking lower increments of x, but higher time scales. So if I jack this up to 10 versus 2, you'll notice that we don't get to see more finer increments. You'll see this red line actually goes a lot closer to the top lines here and reaches steady state faster. That's because we're taking bigger time steps as we increase our R value here, which is 10. Pretty big, or not. There we go. Now we got oscillations. So yeah, I guess that's the last thing I wanted to say. All right, I'll leave this at 2 so that when my video gets checked, you can see the correct graph here. All right, thank you.